So now we can start to do some practice on our aldehyde and ketone reactions. Key thing here with many of these reactions is to make sure that you've identified the nucleophile. And then when relevant, if your carbonyl is conjugated, identify whether that's a nucleophile that wants to add 1,2 or 1,4. And before we get started, we should review what the key difference is. The key difference is that the 1,2 addition happens faster, but the 1,4 product is generally more stable. So if your nucleophile is able to add reversibly, then it'll typically prefer to add 1,4. Now in our first two parts on question 1, we're dealing with carbonyls that are not conjugated, so we don't have to worry about that. The only thing we have to worry about in these first two cases is what's the nucleophile. Well, with KCN, the nitrile is our nucleophile. It'll do a 1,2 addition into the carbonyl, which converts the carbonyl into an alcohol and adds our nitrile. In part B, we have a strong base and this phosphorus-based reagent. And so that should remind us, that combination of reagents, that we're dealing with a Wittig reaction. And the Wittig reaction is a reaction that forms a new carbon-carbon double bond between the carbon of the carbonyl and the carbon that's attached to the phosphorus. We'll review the mechanism later on in one of the other questions, but in terms of just determining the product itself, we should draw a product structure. That again forms a new carbon-carbon double bond between the two atoms we've indicated. Now, in this group, part C is the first question we have where we're dealing with a conjugated carbonyl. Now, I haven't specified the conditions necessarily in as much detail as I might on an exam. Remember that when we're adding an amine, it doesn't just need to be under acidic conditions, but needs to be in a fairly specific pH range. We're just going to assume that we've got that right pH range for the reaction to go forward. Now, in part C, we can see that the carbonyl is conjugated. And the amine is one of the nucleophiles that we've identified, in class as being reversible. In other words, it'll add 1,2, but then it gets kicked out and adds 1,4. That being our 1,4 position. So if this amine adds 1,4, we would get this product. But there's something unusual in this compound. Not only is there one double bond conjugated into the carbonyl, there's two. So could the nucleophile, the amine, add in at this position, which we would refer to as 1,6? And the answer is yes. If you think through the steps of the mechanism for the 1,4 addition, the 1,6 would happen in the same way. It's just extended out one alkene. Well, what would that product look like? It would look like this. Now, is one of those answers better than the other? The answer here is yes. And if we use the logic that we've learned in class, which is that 1,4 addition is favored because it gives you a more stable product, then we would have to come to the conclusion in this case that the 1,6 product is even better. Why is it better? Well, in this 1,6 product, our remaining alkene is conjugated into the carbonyl, whereas with the 1,4, it's removed from the carbonyl. And that extra conjugation is enough to help stabilize the 1,6 product that in this case it would be preferred over the 1,4 addition. Part D is much more straightforward. We have the addition of a secondary amine into a ketone. There's no double bond to worry about. Now recall with secondary amines that the product is slightly different because we don't have that extra proton to remove. And so the resulting product is the enamine. Part E, we have a Grignard addition. Now there is a conjugated group here, conjugated alkene into the carbonyl, but the Grignard is considered to be an irreversible nucleophile. Once it adds in 1,2, that step is not reversible. And so we're not going to be able to get this step to go in both directions. And if that's the case, then it will add in 1,2, and it basically gets stuck there. It can't reverse and go back to give the 1,4. How do we get a carbon group to add 1,4? You should recall from class that we talked about organocuprate reagents, and those allow for 1,4 addition of alkyl groups. Part F, we've given you the starting material and the product, but no reagent. And if you look at this, it looks like it's a 1,4 addition of hydrogen. But we don't actually have a way to do that, nor do we need a way to do that. Because we could also just think of this reaction as hydrogenation. So if we use hydrogenation conditions, as we learned in Organic 1, we can hydrogenate an alkene with hydrogen and palladium on carbon, and that alkene gets converted to the alkane. And finally, in part G, we have just the addition of acid and water, and when added to a ketone or aldehyde, that forms the hydrate. All right, from here we can get into some synthesis. And we're going to go about these the same way we normally do. We're going to approach them retrosynthetically, but as we do each step retrosynthetically, we'll go ahead and fill in the reagents at the same time. If we look at the product, sort of the key functional group in the product is that diol. And we know that we can make diols from a dihydroxylation of an alkene. And in this case, it would be this alkene that would give us the product. How do we do that reaction? Dihydroxylation uses osmium tetroxide and NMO. Now we need to make this alkene. And if this is a case where we want to look at ultimately what we're trying to go back to, notice that we not only need to make this alkene, but at some point we need to add in all of these carbons. Noticing that we start with a halogen, it might occur to us that a Grignard is going to be what helps us to add a whole bunch of carbons. Well, if we're doing a Grignard, one of the common electrophiles that we can add to a Grignard are carbonyls. And that would actually make sense given that we're doing a set of practice exercises on aldehydes and ketones. But even if we didn't know that, we know that probably the most common group to add a Grignard to is a carbonyl, which results in forming a new carbon-carbon bond, as well as an alcohol. And then under acidic conditions, we're not going to need harsh conditions here. This alcohol is tertiary. It's also adjacent to an aromatic ring. It's going to fall apart on an E1 very easily. That gives us our alkene. And then it's just a matter of picking, the correct carbonyl for this Grignard. You can see here we're going to need to add 4 carbons, and we want that carbonyl to be on the second carbon. And then, as we always should, although sometimes we don't remember to include it, we quench the reaction with water to protonate the alcohol. And that's going to be our 3-step synthesis that successfully forms our product here. And we're going to see a lot of similarity on this next question. And the reason for that is, as you may recall, at this point, we still don't have a lot of reactions that make carbon-carbon bonds. In about 2 chapters, when we get to some other reactions of carbonyls, specifically alpha substitutions, as well as condensation reactions, at that point we're going to have a lot more ways to make carbon-carbon bonds, and you might come up with some very different solutions to either one of these questions. So if you were working on these problems, say, studying for the final, you might come up with some very different answers here, which are perfectly valid, but using reactions that we haven't yet learned at the point where this practice exercise is worked into the class. Now, very much like question 2 where we had the diol, here we have a dihalide. And so we know, and just for ease, I'm going to abbreviate the aromatic rings as pH. We know that with the addition of bromine to this alkene, that we can form the dihalide and get to our final product. Now, again, we've got to add a whole bunch of carbons. And in fact, when we look at the way this structure is drawn, we might find that we really can't do it in a single step. But to make an alkene here, we can do it in a couple ways. But probably the easiest way that we've learned to make alkenes that will also help us by adding carbons is using a Wittig. So if we start with that carbonyl, and use the Wittig that contains 2 carbons, strong base, we can get our addition to take place, and we form the alkene that we need to do the bromination. From here, we really need to just add a second aromatic ring. And so if we think about that from our initial starting material, we could add phenylmagnesium bromide to that. That gives us an alcohol, and then just an oxidation gets us to the ketone. So this is another good example where we talk a lot about using retrosynthesis, but sometimes it ends up working that we work from both ends. We start retrosynthetically, we start working our way backwards, but at some point we realize it's actually going to be helpful to work forward. And so we can go in both directions. All right, question 4, we have a series of carbonyls, and the question is which one is the better electrophile? So in part A, they're pretty similar. The only difference is, the second compound has an extra methyl group. But that methyl group is fairly significant. It creates more sterics around the carbonyl. It's also an extra electron donating group. And so both of those factors in general make ketones less reactive than aldehydes. And so our aldehyde here is the better electrophile. In part B, we have two ketones, but we've changed groups. One has two aromatic rings. One has replaced one of the aromatic rings with a methyl group. Well, aromatic rings are resonance donors. The more of those resonance donors that you have, the less reactive the carbonyl will be. And in part C, we have T-butyl groups on each side of the ketone, but in the first structure, they're one carbon further away. And because they're one carbon further away, they have less of a steric impact on addition to the carbonyl, and it'll make it a slightly better electrophile. All right, question 5, we're looking at some Grignard additions. Basically, how do we make these compounds from a Grignard? In some of these, there are multiple possible answers. I'm just going to go through one here. But what we know is wherever that alcohol is, that has to be a carbonyl. So notice when I made that one into a carbonyl, I took away one of the R groups, and that other R group would be our Grignard. Same thing in part B. We're going to make that carbonyl or that alcohol into a carbonyl again. In doing that, we remove one of the carbon bonds to it, and we make that side into the Grignard. Same thing in part C. There's our carbonyl, and that means the other side would be our Grignard. As I said, there's more than one way to do this, and we could have broken up part C in the opposite way. And if we had done so, it would have given us that pair of compounds. All right, question number 6, we're looking for a mechanism. We can see the ylids already formed, so that we know this has to be the Wittig reaction. The Wittig reaction, two-step mechanism. The first step, the carbon of the ylid does nucleophilic attack onto the carbonyl, and the corresponding carbonyl electrons attack the phosphorus. That forms the four-membered ring that we see in a Wittig reaction, known as the oxyphosphatane intermediate. And the second and final step of the Wittig mechanism is that four-membered ring breaks apart, makes the triphenylphosphine byproduct, along with the new alkene. Our final question, question 7, gives us a new nucleophile, fluoride, and wants to know if that nucleophile, when being added to an aldehyde or ketone, would give us a 1,2 addition or a 1,4 addition. How do we determine that? It's all based on how good of a leaving group your nucleophile is. Fluoride, unlike all of the other halogens, is generally a very, very poor leaving group. Because it's a poor leaving group, it'll add 1,2, but that 1,2 addition will not be reversible, and so it will never be able to add 1,4. So that means if we're working with fluorine or fluoride as our nucleophile, we get 1,2 addition as our product.